Hi everyone. In the previous lecture, we discussed what happens when you feed an exponential signal of the type e power s naught of t to an LTI system with a transfer function h of s, and we showed that the output of the system is simply the exponential e power s naught of t multiplied by h of s naught. This is nothing but the transfer function evaluated at the exponent of the exponential. We said if the system has real poles at plus minus omega p, then an input of this type e power plus minus and a real exponential of this type e power plus minus omega naught t omega pt will make the system offer an infinite gain. Okay, so then if you feed this as an input, we said that the system is going to offer an infinite gain. Similarly, we said if the poles lie on the j omega axis, so which means the poles are purely imaginary of the type plus minus j omega naught, then a complex exponential of this type e power j omega naught t or a sinusoid of this type cos omega naught t will make the system will force the system to offer an infinite gain. Okay, or I can say the system is going to offer an infinite gain for these inputs. And we said this is also intuitive because the poles happen to be on the frequency response graph or on the j omega axis. So therefore, if I feed a sinusoid of frequency omega naught, I am bound to get an infinite gain for that. Now in this lecture, we will add certain practical constraints. So we would rather want to see what happens when I actually apply an input at t equal to 0. Okay, so normally if any practical circuit or system, say we are feeding an input from a function generator, so we usually turn on the system or a function generator at some instant, and so the circuit will see as though the input is being applied to it suddenly. So that we are going to say mathematically that the time at which the input is applied as t equal to 0 and that the input was 0 before t less than 0, before t equal to 0. The other constraint that we are going to include is causality. A causal system is one in which the output of that system will depend upon the current and the past values of the input. It cannot depend on the future values of the input. Okay, so that can be mathematically represented can be embedded in the impulse response model by assuming that the impulse response is 0 for t less than 0. So this is a condition for a causal system. Okay, so now using these two conditions, we will see what exactly happens when I feed an exponential signal of the type e power s naught of t. Okay, in addition to that, we will also see how the system, for example, we said if I feed an exponential of this type where the exponent of the exponential happens to be a pole of the system, then the system is going to offer us an infinite gain. So we will see what exactly happens to the system. Okay, will the gain be infinity at t equal to 0, or how does the gain change as a function of time? So that's what we'll be studying in this lecture in a more mathematically rigorous way. So to first capture the input e power, I'm going to assume that the input is now e power s naught of t multiplied by u of t. U of t is a unit step function which is 1 for t, u of t is 1 for t greater than 0 and 0 for t less than 0. The additional condition that we have already discussed is that the impulse response is 0 for t less than 0. Using these two conditions, we will now evaluate the convolution integral, which is e power s naught of t into u of t convolved with h of t. So when I apply the convolution integral, I will get h of tau into e power s naught of t minus tau into u of t minus tau. Now we will apply the definition of a step function, which is u of t minus tau is equal to 1 for t minus tau greater than 0 or for tau less than t. So for values of tau greater than t, the value of the integral will be 0. So which will force the limits of integration to run from minus infinity to t, because the limits of the integration or the variable here is tau. Okay, so for tau greater than t, this integral will be 0. So the limits will reduce to minus infinity to t. Okay, I have again taken e power s naught of t common out, and because t is a constant in this integral. Now we will impose the additional condition, which is h of tau is 0 for tau less than 0. So that's your causality constraint. From that we can see that the limits of the integral will become 0 to t h of tau into e power minus s naught of tau d tau. Okay, that will be your expression. So now you can see that your input signal e power s naught of t is now multiplied by a gain factor. But that gain factor is not a simple, I'm showing it here. So that gain factor is no longer a simple h of s naught, but rather we are leaving it in an integral form like this, because I cannot write it in a simple closed form expression. So now we'll make certain assumptions about the transfer function and try to see if we can reduce this expression to some simple closed form expressions. So I'll first assume your transfer function h of s has n poles. It's only a pole only system. It doesn't have any zeros, it has only poles. And these poles can be complex, and for the time being I'm also going to assume they're all, they can be even in the right or left of plane, they can be anywhere, okay, and the only thing is that system has n such poles. Then you can represent this using partial fraction expansion as a sum of n first order systems, okay. You can just express this as n single pole systems, where all the the poles of those n system happen to be the poles of this n poles of the single system, each one of them being a pole of the system h of s. So if I take inverse Laplace transform of this equation, then I'm going to get h of t as some constant bi times exponential of e power minus spi t. Spi is the pole of the system into u of t. Okay, so this is now my impulse response. So this I'll substitute in this equation which we just derived, okay, and see what happens to the final output. So if I substitute it, I'll finally write the final result here. So if you substitute this, you will actually get two expressions. It's a pretty simple algebra. You can probably pause the video and just look at the steps. It's a very simple mathematics here. You will actually get two terms, which is the first term is simply e power s naught of t into h of s naught, which is your Laplace transform evaluated at s naught, which is what we did. We got it in the last lecture. And we also have a second term here. This is entirely determined by the poles of the system. So you have actually a sum of exponentials multiplied by some constants. Okay, and these exponentials are nothing but the exponents of the exponentials are all the poles of this system. So now, if I assume the system to be a stable system, then we know all the poles are in the left of s plane. So all the exponentials are going to decay down to 0 as t tends to infinity. So in the steady state, for a very large time, I can ignore this term. This term will go to the second term will go to 0. So you'll only be left with the first term, which is e power s naught of t multiplied by h of s naught into u of t. Okay. So in the steady state, so what we discussed in the previous lecture, we said we only wrote this as an expression for the system with e power s naught of t as an input. But now we actually see that this is a steady state response. In fact, if the system is unstable, even though h of s naught can be finite, if it's an unstable system, the second term here, this term here, will not go to 0. It will rather grow unbounded and the system will become unstable. Okay, so this is a more general expression for an n-pole system. In one of the previous lectures, I had derived a similar expression, but using the knowledge of the step response of a simple first order system. From that, we just extrapolated and said, okay, the expression might look like this. Okay, but here we have given a more rigorous proof of the actual response for a causal system to an input starting at t equal to 0. Now we'll make some few approximations. So now we will start analyzing it. What happens when your S naught happens to be a pole of the system, SPK. So here if you see, the poles of the systems are SPI. Okay, these are the poles of the system where I going from 1 to n. Your input S naught of t happens to be one of those poles, SPI or SPK here, where I equal to k is the location of the pole. Now you'll have to substitute this in this equation. Again, I'll quote the final result. What exactly do we get, and then we'll try to interpret the final result. Again, it's a very, very simple algebra that you'll have to go through. You can just substitute this in the integral here, and you should just substitute S naught as minus SPK, and you can derive the expression. I'll finally talk about the final result. Okay, so here if you see, BK here represents, so as we said, your transfer function h of s can be represented as a sum of n single pole systems with coefficients given by Bi. So this will be S plus SPI. Okay, so your BK is the coefficient for the kth pole, the pole SPK. Okay, so you will get this term, which is your input, e power minus SPK is now your input, multiplied by BK into t into u of t. and then you will get a set of terms. So this term, if you see here, this is nothing but your input e power minus spk of t multiplied by this expression, summed over bi by spi minus spk into u of t. If you closely observe this equation, it is nothing but h of minus spk, except we have removed one term from this, which is the term corresponding to this bk upon spi plus spk. Spk minus spk. We have removed that term from this. Okay, because obviously that term is going to blow up to infinity, and that is taken care of in this integration. So that term is removed. And similarly, the third term here is comprising of exponential signals with the exponents equal to the poles of the system, except the pole spk. Okay, there is no spk here. I is not the summation here excludes I equal to k term. So that's the only difference. If you see the previous expression, this term was absent, and we used to have I equal to k in both these terms, the second and the third terms. Now we will see what happens for a stable system. We said all the poles will be in the left of S plane. So these terms will eventually, in the steady state, will go to 0. So all these terms, because they are all decaying exponentials, they can even be complex poles. Okay, but if let's say the poles are on the j omega axis, then it's a marginally stable system. So you will have some kind of an oscillatory response. Okay, but if they are all in the left of S plane, all those poles will vanish to 0. Eventually all the exponential signals will go to 0. Now you are left with only these two, the first two terms. Now if you look at the second term is a constant. You are just multiplying your input e power minus spk of t with some constant. This is a constant. It's independent of time. But if you look at the first term, we are multiplying it with a time varying gain bk into t. Okay, so if I've shown it in the graph here, so you have two functions. One is a constant, and the second one we are multiplying it with t into u of t. Okay, the exponential is same. We are multiplying e power minus spk of t, one with a constant, other with this function. In the steady state, of course, t into u of t is going to be significantly much larger than the constant, so we can ignore the constant term. So we will be just reduced to an expression like this. Alpha is a constant, some constant, e power minus spk of t, which is the input, into t into u of t. So now this can be seen as though the system is the input, the system is offering a time varying gain, and this gain will approach infinity in the steady state. So as t tends to infinity, the gain of the system also tends to infinity. Now if you assume that the system has small n number of poles at spk. When there are multiplicity of poles at the same point, instead of just here we assume there is only one pole. In that case, again you can follow a similar derivation that I have shown here and show that the expression is going to be e power, the input e power minus spk t multiplied by t power n by n factorial. So the gain is actually going to grow exponentially. So this is the expression for gain here. Okay, so now I'll actually talk about this term. So what we discussed, the main point that we discussed right now is if you assume a causal system and the input starting at t equal to 0, for a single pole system with one pole at spk, we said that the output will be of this type, e power minus spk of t into u of t. And we said that the gain offered by the system is time varying, and as t tends to infinity, the gain tends to infinity. So I'll discuss one example. We had already discussed this example in the previous lecture. We said we took a system with a complex poles and we fed a periodic signal to the system. And if you see, intuitively we explained that the amplitude of the sine wave or the output will grow linearly. So that is nothing but, it's as though that's nothing but this function shown here, t into u of t, which we derived in a more mathematically rigorous way. And we are just saying, I'm just trying to say that it's exactly corroborating what we had intuitively discussed in the few lectures ago. Okay, so this is what happens when you actually feed a singular input to a causal system. So all we are saying is that the system is going to offer a time varying gain, and the gain will increase linearly with time if you have a single pole at the exponent of the exponential signal. If you have a multiplicity of poles, of course it's going to increase at a much higher order, the higher rate, the gain. Okay, as a function of time, it's going to increase at a much higher rate. So we'll take some examples. So I'll start with a simple example, which is I'm applying an input of this type, e power minus a into u of t, to a system with pole at s equal to minus a. So we can directly write the input is going to be e power minus at into t into u of t. Okay, in the steady state, this is the input. In fact, for this system, since it has only one pole, if you just look at this expression, it might be a little complicated, but the expression that I've shown here, containing 3 terms, there will be no second and third terms because the system has just one pole. All the other poles are non-existent here. Okay, so you will have only the first term in this expression. So that's why we can directly write this as the expression for the output. See, this output expression, you can also derive it using Laplace transforms. Okay, from the theory of Laplace, you can find the Laplace transform of this and multiply it with this, and you will get this as your answer. But here I'm trying to give more of an intuitive explanation from the mathematical analysis that we just carried out a few moments ago. Now, which is, if I'm showing it graphically, I've applied a decaying exponential signal. The output of the system is going to, say it's multiplied by t into u of t. The system is offering you an infinite gain in the steady state, but by the time input has already reached 0. So the output will also be 0. Okay, so even though the input, I mean the system is actually here, the gain offered by the system is really large, it is actually t. Okay, but then the input has already gone to 0 at that point. So a large number multiplied by a small number depends on, so now see this is a very interesting problem. What happens when I multiply 2 signals? One signal is increasing but the other signal is decreasing, then what will be the final value of the signal? So that is determined by the rate at which the 2 signals are increasing and decreasing. So in this case, the function is increasing linearly, but e power minus at is decreasing exponentially. It's a much faster decrease. So when you multiply it with an increasing function, you can say that the overall function will also be decreasing. Okay, because the decrease of the exponential dominates here. So I've shown a very simple theorem here, so which is limit of t tending to infinity, f of t into e power minus at. So I'm multiplying a function with an increasing function, f of t, as a function of time with e power minus at. And if this limit tends to 0, then such functions are called functions of exponential order. So these functions are increasing, but they don't increase at a rate greater than the rate of decrease of an exponential function. Okay, or I can actually write this way, f of t divided by e power minus at. So if you see, now both are increasing functions. Exponential function will increase at a much faster rate compared to f of t. Then we say that this function f of t is a function of exponential order. All polynomial functions of the type t power n and sinusoidal function cos t and sin t, they all obey this. They are all functions of exponential order. Okay, so if you feed an decaying exponential signal, eventually the output will also be 0, but you should keep in mind the system is actually offering you an infinite gain. But since the input itself is 0, the output will also go to 0. The next problem is we are going to assume a right of plane pole system with a pole at s equal to plus a. So the singular input for that is going to be e power plus a t into u of t. So when I apply this as an input to the system, the output is again going to be t into e power at into u of t. Okay, so I've actually shown here the input in the dotted line, and this is the output. So of course initially, since you are multiplied it by t, the output is going to be 0, but eventually your output is going to grow much faster than the input because it's multiplied by a factor t. Okay, so your output is going to reach infinity in the steady state even before input reaches that value. The third example is something we have already derived in the previous lectures intuitively, but now we can even mathematically show that if I fed a signal cos omega naught t into u of t as an input to this system, then the output will simply be t sin omega naught t into u of t, where t here, t into u of t, is the gain offered by the system. This is the steady state gain offered by the system. Okay, so this is an exact expression. T into sin, if you can actually derive it using, because it's a very simple system, you can actually derive this expression. Since it has just a complex pole, only one set of imaginary poles, complex conjugate poles, Okay, so it's simple, you can derive it. But if the system had many more poles and just one complex pole like this, then, and all those poles are on the left of S plane, then in the steady state we can say the expression will just reduce to this. So that's the whole purpose of this analysis. Okay, it was actually to say what is the steady state behavior of the system when you feed a singular input, or an input where the system has a pole. Okay, so in the next lecture I'll talk a little bit about zero forcing inputs, and we'll similarly analyze how does the system behave when I feed zero forcing inputs as an input to the system with these practical considerations.